Hello, everybody, and thank you for joining. My name is Raphael Motafort. I've been a researcher at NREL for just over 7 years, and for the majority of that time, I've worked on specific computational models, but lately I've been leading an effort to characterize the portfolio of wind energy software supported by the US Department of Energy. As part of that work, we've hosted a series of 4 workshops over the past 2 weeks, and today's is the last one. And what a shame, because I'm just getting used to giving nearly the exact same presentation multiple times a week, very early in the morning. But more seriously, many of you have joined for a few of them, and some of you have even joined for all of them. So I just want to say thank you. I'm really appreciative of your interest and attention in these workshops, as well as your patience in the repeated portions at the beginning of each workshop. In any case, this one is focusing on the software related to the OpenFAST ecosystem. And some of my colleagues from NREL are co-hosting this workshop, and they are Pietro Bortolotti, Garrett Barter, Jason Yonkman, Derek Slaughter, and Dan Zalkind. And before we proceed, I just want to give you a heads up that this workshop is being recorded, and the materials, the slides and the recording will be made available online afterwards. I just will go over the agenda here quickly because it's changed slightly since I sent out the initial invite. We'll start with this intro, and then there's an overview section of the portfolio of wind energy software that we call the WETO Stack as a whole. And then there will be a very short poll on these workshops in general and the WETO Stack. And then we'll move into presentations specific to OpenFAST, ACDC, and ROSCO. And then there will be an opportunity after that for another poll, a bit longer one there, and then a longer portion of community discussion. And I just want to point out that we allocated a majority of the time for this sort of community discussion and polling. So for us to have this two-way communication between the model owners at the labs and you, the user community. So yeah, here's your chance, and we're really excited about it. So yeah, please engage and let us know what you think about this work. So quickly, I'll introduce the Holistic Modeling Project, which is the effort at NREL that has supported putting these workshops together and doing this whole study. So the primary funding mechanism for wind energy research in the US is through the federal government's Department of Energy, and specifically the Wind Energy Technologies Office. And this is, the acronym for that is WETO. So this is the WETO in WETO Stack. WETO's mission is copied here, and it's quite long, so I won't read it, but I'll just summarize it in that WETO invests in wind energy research, development, deployment, demonstration, research, development, demonstration, and deployment activities that enable and accelerate the innovations needed to advance wind energy. And in today's world, these activities nearly always involve using or creating scientific software. So you can maybe rephrase that as WETO invests in wind energy software that enables and accelerates wind energy. The scale of the wind energy research supported by WETO is quite large. And here on the right, I'm showing a list of active projects only at NREL. And yeah, I just wanted to communicate that there is quite a breadth of work happening in the wind energy space funded by the US Department of Energy. And many of these create or extend software models as part of their work. The WETO project portfolio spans many national labs, and the ones listed here at the bottom have contributed directly to the WETO Stack. Now, because of this breadth of research, there are many software tools, and historically there's been little cohesion or coordination across them. And for that reason, the portfolio coordination task of the Holistic Modeling Project is working on addressing this problem. We're in the process of shifting to a new paradigm where our computational models fit better together and the collection of software moves forward in sync. It's a 3-year project. We just finished the first year, and it was primarily around getting data in place and engaging with model owners. And the current year involves using the methods developed in the first year and engaging with the community of users. And that's exactly what these workshops are. And then the final year will involve additional portfolio streamlining and putting a coordinated roadmap in place. So I hope that sets a little bit of context, and now I'll describe the WETO software stack as a whole. Here's a map of how the software in the WETO stack are grouped for these workshops. We tried to group them more or less by the context in which they're used, and that's mostly to have better alignment with the audiences that attend the workshops. So just to set the stage for the next few slides, I want to describe these groupings at a high level. We'll start with the TEA, the Techno-Economic Analysis and Cost Models here at the bottom. And this group of software allows for estimating the capital costs and operating costs to ultimately determine whether and how to develop a wind energy project. Then there's the software for wind farm analysis and controls, and these allow for doing a low fidelity estimate of energy production. So maybe after a first sanity check with the TEA and cost models, you might use the wind farm controls and analysis tools to start to put together a schematic design of a wind farm. And then there are the mid-fidelity tools, and these are mostly what we'll talk about today. They're all lumped within the OpenFAST category since they're used primarily within that ecosystem. And here you can do a more detailed design of a wind turbine and a wind farm. And then the systems engineering tools are a group of optimization-oriented software with varying levels of fidelity. And they work closely with OpenFAST tools to do whole system optimizations of wind turbines. And then finally, there's the high-fidelity models that enable detailed aerodynamic or structural dynamics. And these could be used to research or design any next generation technologies like farm level flow control or blade treatments for improved aerodynamics. So I wanted to just give a kind of an idea of how these all fit together. So I hope that gives a little bit of context. And now I'll talk through each of the software groups more specifically. These are the systems engineering tools. I borrowed this graphic from the Big Adaptive Rotor project, or BAR. And I just thought it was a really nice diagram to show how all of the tools kind of fit together in a workflow. So I'll start describing this with WISE, which is the lighter yellow box here, kind of encompassing some of the other ones. WISE is a powerful design optimization tool, and it has a lot of capability, but its core design intent is to enable controls co-design, which is the coupled optimization of the hardware and the software of a wind energy system. This is especially important in floating offshore wind turbines, and this is one area of focus for WISE. WISE integrates with Wisdom, which is here on the top left, into its design loop. And Wisdom is another optimization tool with lower fidelity models tailored specific to systems engineering. And WISE couples Wisdom with OpenFAST and ROSCO, and those are two tools we'll talk about today, as part of the WISE design. And in this workflow, you can add PyNumad, that's down here on the bottom left, to the workflow to do a higher fidelity detailed design of the composite structural model of the rotor. And then WindSE is another software in the group down here at the bottom. It's a RANS CFD model that's designed specifically to strike a balance between the engineering scale models and the flow resolved CFD. It's tailored to specific optimization problems. It's not quite tightly integrated into this workflow yet, but it still fits into this category nicely. The techno-economic analysis and cost modeling sets of tools can be similarly mapped. This diagram shows the tools used in different areas of cost modeling in order to ultimately estimate the total value for wind energy assets. So I'll start here on the right to describe this. WAVES is a software that models capital costs, operating costs, and energy yield to determine a total asset value. It gets the CapEx estimate from either land-bossy, hybrid-bossy, or Orbit for land-based hybrid power plants or offshore power plants. And then Coral is an add-on to the offshore, to Orbit, for the offshore balance of system costs to account for shared system installation infrastructure. WAVES gets its OpEx estimate from Wombat, and it uses Florist to estimate energy yield. Florist is outside of this grouping, but it is integrated into this kind of workflow. And then Narwhal, up here on the top right, is a library of cost equations for offshore wind farms, and it uses some of the other tools here to develop its library of cost equations. The next collection of software are the wind farm analysis and controls and control models, and these are mostly related to characterizing and improving the energy yield of a wind farm. Florist is a steady state wind farm wake modeling software. It's very low fidelity, but also cheap to run and highly tunable to existing data. Its core capabilities to establish the energy yield of a wind farm given a set of wind conditions. And this is often used to optimize the wind farm layout or design wind farm control strategy to mitigate wake losses or any other kind of operating losses. Flask connects Florist to field data, it facilitates working with SCADA data to enable wind farm model validation by connecting directly to Flores. It's also used for field experiment design and monitoring. And then OpenOA is an operational assessment software that provides common data structures and methods for analyzing wind plant operational data to determine wind plant performance. It's specifically been used to identify a variety of operational losses, and there are examples of this using open data sets included in the OpenOA repository. And then Hercules, just listed here on the right, is a real-time simulator for wind-based hybrid power plants. It integrates with AMR Wind, which is a high-fidelity wind farm aerodynamics model in another group of software within the WETO Stack. And so it integrates with AMR Wind to simulate a power plant combining wind and solar power production and energy storage. And there's an associated wind hybrid plant controller, and that's kind of like the bread and butter here. It's really trying to develop the wind plant controls so that to study wind plant controls and how they can be used to balance the other system costs in this hybrid power plant. Here's a basic map of the OpenFAST collection of tools. And of course, these are the ones we'll focus on today. And Jason and the others will do a much more thorough job of explaining these. So I'll skip over it for now entirely. And then the last grouping of tools here are the high fidelity models. And these tools are all CFD codes addressing specific components of the wind energy simulation cascade of scales. At the largest scale is ERF, which is the Energy Research and Forecasting Model. It's an atmospheric model and couples the mesoscale to the microscale. It's capable of simulating regional scale weather, and the target domain size is between 10 and 1,000 kilometers. ERF couples with AMR Wind, which is a model for the atmospheric boundary layer, and its target domain size is less than 10 kilometers. AMR Wind can use the regional weather model from ERF as a boundary condition or forcing function for its own simulation. And then going down another scale, AMR Wind can couple to NALU Wind to do a fully blade resolved simulation. And the target domain size for NALU Wind is less than 1 kilometer. AMR Wind and NALU Wind together are referred to as ExaWind, owing to their development within the Exascale Computing Project. And all of these software are GPU compatible and support both workstation and HPC use. And then I'll just point out a relatively new project that isn't listed here is called OpenTurbine, which is a structural model specifically designed for integration within ExaWind. It's in active development for the next couple of years. So there's not too much information to share now, but there is a high fidelity modeling workshop was planned for this week, but we had to postpone it just due to scheduling conflicts. But we're planning to do that later in the summer, and you can look out for that to get some more information on OpenTurbine. Okay, that's the overview of the WETO software stack, and now I've got a quick poll just to get a little bit of an idea of where we are relating to these workshops. So you should see this coming up on your screen here in Teams.
Showing up, please. And then froze.
See some results coming in. So just give just another minute.
Yeah, there's some funniness with the polls today too, Ralph.
That's too bad.
Can you get it to work?
Or my second one doesn't seem to work for me.
Interesting. All right, well, we're getting close to 20 responses. So maybe we can call it that. I'll leave it open if you want to, yeah, I don't know what it looks like on the back end or on your ends, but if somehow it comes through in the end, yeah, feel free to respond later on. Yeah, I see only 2 groups in the second question are coming up. There was a trick question, trick answer in the first one on how many WETO software workshops you've attended, and nobody bit. So that's good. You're all paying attention. Okay, with that, I'll turn it over to Jason. Talk about the OpenFAST toolchain, and yeah, you can take control, Jason.
Okay. Thanks, Ralph. Yeah, we'll proceed and talk a bit about jumping into where we are with OpenFAST these days. Let's see, how do I advance slide? Okay. So probably most everyone attending is familiar with basically what OpenFAST is. Really brings together the aerodynamics, hydrodynamics for offshore, of course, the control system, and the structural dynamics of the system to do full aero-hydro-servo-elastic analysis of a given individual turbine. That turbine could be land-based, fixed bottom, offshore, or floating. And we basically have 2 ways to run OpenFAST. One is the typical way of basically trying to march in time, capture the effect of the turbine to wind and wave excitation, with the goal of basically doing load analysis following things like IAC standards. So the goal of really calculating ultimate and fatigue loads in the system. And the second approach that we use with OpenFAST is basically at any point in time, you can pause the model, usually at some steady state or periodic steady state condition. You pause the model, what we call an operating point, and then we linearize about that point and basically export a linear equivalent system, like in state space form, ABCD type matrices. And if you have a linear model, I would say you can really understand what the model is doing. You know how inputs relate to outputs and states, and you can use that for modal analysis, identifying mode shapes, natural frequencies, damping ratios at various conditions. You can use that for controls, design, or aeroelastic stability studies. Let's see. This is a slide that kind of shows sort of core modules of OpenFAST. OpenFAST is basically a very modular architecture. And yeah, BeamDyn is like our high fidelity beam type model based on geometrically exact beam theory. Elastodyne is our sort of original structural dynamics model based on some combination of multi-body and modal type formulation, although it's not fully linear. There's quite a few nonlinearity terms in Elastodyne. But if you're familiar with tools like Flex 5, that's very similar. Subdyne is our structural dynamics module for the support structure. That's fully linear in the sense of beam elements and linear elasticity. We do support in Subdyne Craig-Banton reduction. So you could take a model like that semi-submersible that likely has 1,000 degrees of freedom for all its elasticity and reduce it down to its sort of core modes, the guide modes, plus some. There's a question there. I'm not exactly sure what that means, but let's see. And then we have a Servodyne is really our controller interface. There's a few built-in options in Servodyne, but mostly as an interface for user-defined control because controls tend to be the sensitive part of the wind turbine system. On the flow side, we have Aerodyne. That's our main aerodynamic solver. Has either blade-out momentum theory with a bunch of advanced corrections, or a free vortex wake model called Olaf is built in there as well. Inflow wind basically just processes the inflow, like from TurpSim. And Hydrodyne is our hydrodynamics module for offshore, really with a hybrid combination of potential flow and strip theory. looks like one person's having trouble with slides, but hopefully the rest can see it. And then we have two core mooring modules with Moordyne being our core lumped mass approach. MAP is really a quasi-steady model. Okay, give a quick update on some things that have been happening recently in case you're not fully aware. First of all, we've been working a lot on aerodynamic stability calculations and being able to introduce aerodynamic options that are linearizable for things like stability. And unfortunately, it looks like my the dot product there is not showing up correct, but that should be x dot where the ampersand is. But we have both linearization of things like dynamic inflow and the unsteady airflow aerodynamics, which then means that your state space model can have aerodynamic states in them that are really useful if you want to calculate, say, aeroelastic stability of an operating turbine. We've also done a lot of work with our BEM solve recently for both high shear and highly skewed flow. This is showing an overall improvement we've seen from the old to the new. I think the old code basically had a cosine to the cube effect with skew angle. And from vortex theory or high fidelity blade resolve theory, we've shown that we were basically over predicting the effect of shear on things like power and torque and thrust. And with some new corrections we've made, Emmanuel Brandler presented this at Torque a few weeks ago. We have quite a bit of improvement relative to high fidelity codes now. For those in the distributed wing community, we've also done some work recently on tail fin aerodynamics, and so again, mostly useful for those in the small wing community. For those in the floating and offshore communities, I think we've done a lot of work in the last couple of years. One is we can now do full structural hydroelasticity now of the floater. So you can treat the floater as a series of beam elements or cable elements interconnected by various kinds of joints, not just cantilevered. We have ball joints, pin joints, universal joints, and so on. And you can reduce that structure down and get to capture the core fundamental modes and have all hydroelastic effects included. That's really for the purpose of calculating internal member level loads in the floater. We also introduced constrained new wave theory. That's really about taking an irregular sea state, for example, this 50-year irregular sea state shown here, and being able to embed the extreme wave that happens. So statistically equivalent, but we can ensure that any given stochastic utilization has some extreme wave event in it. That's really useful to sort of, rather than waiting by choosing seeds, enough seeds, by eventually you get the big wave to show up. Now we can basically force it at any time. So this is showing all these sorts of irregular sea states with the same sort of big wave embedded in. We've also introduced in our strip theory formulation the McCormick-Fuchs diffraction correction. That's really useful for things like gravity-based foundations, or if you're doing a semi-submersible and just want to do strip theory, being able to do that without having to do a full potential flow solve. We've also worked a lot with large displacement now. In the 4.0 release of OpenFAST coming out very soon, we have a full 3D wave grid now defined, where basically the structure as it's floating around in the domain, it used to solve just wave kinematics at the undisplaced position, and now you can have large translation, and soon to come is also large yaw rotation, really enabling large motion in the fluid domain and all the phasing and so on that comes from that. With this grid, we were easily able to add lots of different wave stretching options. So extrapolation, Wheeler, vertical stretching are now things we can do. And coming soon, likely after 4.0, but hopefully later this year, we're introducing not just in the strip theory solution, not just cylindrical type structures, but also full support for rectangular cross sections, which we think will be quite useful for many systems like this full turnus floater. On the servo dynamics side, we've introduced lots of active and passive control options. So you can now basically anywhere in the system, blades, nacelle, tower, substructure, place as many actuators as you want. Things like tune mass dampers, in one direction or omnidirectional. They can be fully passive or semi-active. You can also place 2 liquid column dampers in the system, again, as many as you want, wherever you want in the system. For offshore systems, we've introduced buoyancy cans into the model. That's useful for things like this spider float developed by Sinu Srinivas. And then on the mooring system, things like these sea spring systems that introduce some nonlinearity in them to mitigate extreme extreme mooring line snap type loads. Really helps with that. And so these elements can now be placed in your Moordyne model. And we also have things like active cable tensioning, where if you have cables within the structure or in the mooring system and you want to sort of actively change their length, you can now do that through a control interface. And so all quite a new features on control. On the mooring side, also quite a bit of extensions here. I'm not an expert on these topics. Matt Hall has led the team doing this, but we've introduced synthetic viscoelastic materials, quite useful for synthetic ropes, basically combining a low frequency and a high frequency effect. Used to always have to do these sort of simulations in 2 steps, and now you can do them basically in 1 simulation, which is quite nice. They've also introduced the mooring system ability to do full seabed bathymetry and various kinds of friction models that allow you to really represent the terrain on the seabed. We've also introduced basically a bending stiffness option in Moordyne, which is really important for the dynamic power cable. Coming very soon, I think in the 4.0 release, is also being able to do basically mooring line failure simulations, where based on some given time or like a tension threshold, you can basically have a line break and then watch the system respond to that. On the coupling side, we're very excited to introduce basically what's coming out in OpenFAST 5.0, hopefully in September this year. We've introduced a new tight coupling option. So for those familiar with the background of OpenFAST, we have this loose coupling framework where every sort of module gets integrated together, but each one has its own time domain solver. With tight coupling, we've basically taken the integrator out of some of the modules and do that at the glue code level. With that, we've introduced a new generalized alpha-based method. And what we're seeing is that greatly improves the performance of OpenFAST, leading to 10 to 100 times faster than previous models. And so we're quite excited to have that come out and make OpenFAST. A lot of people complain OpenFAST has gotten powerful but slow, and so we're hoping to come back on that with speed here. Another thing we're working on with Envision Energy is a direct steady state solve, basically bypassing this transient that you always see in a simulation and starting directly at a steady state. Useful for sort of minimizing the transient in a time domain simulation, and also directly jumping to the operating point for linearization. Another thing I'll be presenting at NUIA conference next fall is multi-rotor capability. FAST is very modular. We've basically taken advantage of that here and can dynamically allocate instances of modules, and we're able to couple that with our subdyne model as well. So basically do multiple rotors on the same support structure, and things with Olaf aerodynamics really making that possible now. So yeah, not obviously a fairly niche market for that, but nevertheless, people are becoming quite interested in that as you go offshore, and the size of turbines is a limiting factor. Jumping a bit now to Fast Farm. So for those of you who are not familiar, Fast Farm is basically our wind farm extension of OpenFAST, bringing the idea of loads analysis for a turbine to the full farm level. Basically with Fast Farm, hopefully I can get that started. No, I can't get the animation to play. I don't know if you can do that, Raphael, but yeah, for some reason I can't click on that. But anyways, that's showing a simulation of 36 turbines in the Awaken wind farm in Oklahoma. Basically, every turbine in the wind farm can be a full OpenFAST model, and what Fast Farm brings is all the effects that couple those things together, like the full wind farm flow, inflow, the wake effects coming off each wind turbine. And if you want to do things like, wind farm level control, you can implement that in Fast Farm as well. It's not a full CFD type solution. Obviously, if you want to do that, you can switch to AMR wind or Nala wind. But here we really have an engineering model for the wakes, so we can also do this quite computationally efficiently. Some of the novel characteristics of Fast Farm, again, we sort of carry the idea of the modularization framework of OpenFAST to the farm level. We've introduced modules for the wakes and the full array effect, as well as the supercontroller. We have, Fast Farm is based on dynamic wake meandering formulation, and we've done a lot of work within NREL to sort of calibrate the model to best match large eddy simulation. So really trying to do high fidelity simulations much cheaper. Again, you can do a wind farm level controller. We've introduced recently shared mooring systems. So if you have multiple turbines that get connected not just by wakes and control, but also through some station keeping system, you can do that now in the solve. And to make it efficient, we have it solved in parallel mode if you wanted to run these simulations quickly. So some of the things recently going on Fast Farm. One is on the near wake correction. We realized several years ago that our model was breaking down if you had high thrust conditions. We based that on the fact that Fast Farm has had some momentum assumptions in there, and so we've now fixed that by basically having a semi-empirical model that matches at least the mean effect of the wake breakdown in high thrust. We've also introduced a curled wake model into Fast Farm for things like wake steering. Often you want to do in a wind farm, flow control where you yaw turbines, let the wakes deflect and curl away around downstream turbines. And we've introduced this curled wake model now into Fast Farm. So you can do that dynamically. This is just showing the transient effect that you see with a curled wake. We do obviously miss some details. If you have a step change in yaw, you get this big vortex structure that we see in CFD. We don't capture that big vortex, but we do capture the timing of the response of the wake. Presented a couple weeks ago at Torque, our new wake-added turbulence model. This is quite useful if the ambient turbulence level is fairly low, say less than 10%. What we find is that the wake breakdown leads, the shear layer in the wake basically leads to turbulence, which can be quite important to the loading of downstream turbines. And we are basically showing an underprediction of fatigue for low TI before this change. And when you add this wake effect of turbulence, wake added turbulence in there, it really helps bring the fatigue back to what we expect it to be. As I mentioned before, we also can now do shared mooring systems in Fast Farm, where every turbine basically has connections together, not just through wakes and control, but also through additional mooring lines. A big part of our effort is also not just developing new capability, but also doing verification, validation. Just have a couple highlights here of what we're doing. One is our big raw experiment that happened down in Texas, where they took the PE 2.8 megawatt turbine and they tried to throw as many instrumentation and sensors at it as they could with a high characterization of the inflow, things like scanning, LiDARs, radars, met towers, of course, profiling LiDARs, not just of the inflow, but also of the wake. So things looking backwards and tracking, So what we're trying to say is if we really know what the inflow is, can our models predict what the response of the turbine is and what the wake is? You can see the turbine is also speckled. So we have, photogrammetry trying to measure deflections and so on as well. So really trying to capture the full aeroelastic response and do not just statistical validation, but full time result validation of inflow to response. Within the IA Wind Task OC6 project, a couple of things that happened recently, validation of OpenFAST for things like a turbine that's surging and pitching offshore, mimicked here in the wind tunnel through an actuated system. We also did some work validating our hydroelastic capability, say with this tank test of the Tetris bar design. On the fast farm side, some nice work with our partners at Stuttgart doing validation here at the Alpha Ventus wind farm, basically flow through the FINA 1 Met Tower through turbine AV4 hitting AV5, and this is showing the effect of tower base loads and overall, at least again with overall a very good agreement of fatigue loads relative to measurements of the downstream turbine. We've done work recently also now trying to make sure fast farm works with the floating context, and they're showing some validation against our LES code SOFA for things like the vertical deflection and meandering of the wake for floating cases. Jumping a bit to workflows, and maybe I need to speed up a little bit here. Again, lots of things to cover, but just trying to summarize things. Hopefully, people attending are generally familiar with OpenFAST. I would say the overall workflow, of course, with OpenFAST is to be an engineering tool to advance wind technology. And because we're not fully resolving everything, we rely on a combination of things, really calibrating coefficients with, say, high fidelity data or computational solutions or measurements. We bring, of course, any sort of new technology innovations that come down the pipeline. We want to make sure the tool can analyze those things. And a lot of our, of course, processes are based on what the standards require. And, looking at the applications of fast farm, it's really about advancing the technology of wind, looking at novel concepts, sensors, offshore structures, and of course, moving from turbine-centric to farm-centric design. In terms of the overall workflow, obviously OpenFAST is there in the center of the analysis. OpenFAST, as everyone knows, requires lots and lots of inputs to be defined, from the airfoils to the structural properties, controller, the inflow, and so on, hydrodynamics, and so on. And we've developed a number of preprocessors, airfoil prep being a sort of core preprocessor for the airfoil data, taking basically 2D, wind tunnel type data and extrapolating to 3D for rotational augmentation and doing things like unsteady aero models. TurpSim, or the MON model used for inflow generation. ROSCO, Dan will talk about that, really our sort of baseline controller for wind. Of course, you can have your own controller if you're in industry. On the structural side, codes like PyNumad that Raphael mentioned, or AMBA4, used for things like structural analysis, perhaps could also fall in that mix. And then compute mode shapes, the old code B modes is often used, but I think we're trying to replace that with this PyFrame 3DD. And then in terms of the post-processing side, big output of OpenFAST is time domain responses, and there's a number of tools used to post-process that. Raphael, yeah?
Just 5 minutes left, just heads up.
Okay, I'll move on. And then another big output, of course, of OpenFAST is linearized models and MBC3 transformation there, and our new ACDC tool that Derek will present coming up here soon. And then the other big output of OpenFAST, of course, being either stick figure or surface type, visualizations of the structure, which we often use open source tools like ParaView to analyze. Big workflow, of course, is nonlinear time domain simulation. Usually you're following things like the IAC standard for running through all your sort of load cases from operational, non-operational cases, really with the goal of predicting what your loads are and the tail end loads, hopefully, which are less than your resistance of the material. And typically you're using some sort of script that runs all those cases, likely in some high performance computer or some cloud computing environment. And of course you can predict time domain simulations, but often in the end you post-process that with statistics or PSDs or extreme events or something. Linearization, again, is the other big analysis approach. Again, sorry for the ampersands there. Basically taking the nonlinear formulation that's in OpenFAST, doing some perturbation on some operating point, and then representing the solution as a series of perturbations. And with A, B, C, D basically characterizing the full system response. And OpenFAST really generates these models for you then, but of course the user has to ensure that you're at a good operating point because the model is only valid for small perturbations about that operating point. You can use those models, of course, to do things like, Campbell diagrams, natural frequencies as a function of speed or wind speed, damping ratios as a function of wind speed. Of course, you can also do those calculated things like control derivatives, distribute change of thrust with pitch or thrust of wind speed or so on. Two other type of analyses we've been doing a lot of recently is one is sensitivity work to try to figure out, there's thousands of inputs to OpenFAST, what really matters in your design. We've been using an elementary effects approach to look at that, basically looking at, if you have perturbations of input, that leads to perturbations of output, and which ones really, which ones are most sensitive. And so we look at not just the gradient of input to output, but also, how large the range of that input would be. And that kind of dictates, if you sort of look at the tails of that distribution, you figure out what's highly sensitive. And we have a number of publications on that. Another new direction we've been pushing is on use of OpenFAST, not just for design applications, but also digital twins, basically using OpenFAST as a virtual sensor. So combining the OpenFAST model with actual measurements from the asset, with things like a GPS unit or SCADA data that you may have on an asset, and combined with the OpenFAST model, using that to basically use it as a virtual sensor, so you can output things like the tower moments or blade moments that you likely can't measure on all assets. And we're hoping to use that for O&M type applications. So more to come on that. At the basic level, I think everyone's familiar, how to run OpenFAST. It's basically a command prompt driven solve where you define input files and it generates output files after running it through a command prompt. Usually, that's just showing how to do it manually, but likely you have a script running all the cases in the background. So WISE was mentioned earlier by Roth. That's our main script now that we do for turbine optimization. You can also just do it for executing IAC load cases. We're adding support for most of the IAC load cases in the current version of WISE. And but if you want to do more than that, you can also feedback in the process and do full optimization of the system. Just want to also mention we have this OpenFAST toolbox in Python that we have a lot of scripts for basically setting up models, running the simulations, and post-processing the results. Once we get to the poll coming up here soon, we'll talk a bit about roadmap. I don't know if Raphael, if you want to keep going here or bring this up later, but
yeah, we're out of time, so I think we should shift to the other, excuse me, the other tools. And then if there's time on the back end, we can bring this up again, especially for the discussion. So I think this might be.
Yeah, why don't we switch over to, well, I don't know what it is. Yeah, let's switch over and I'll introduce this right before the poll then.
Yeah. All right, Derek, you'll have to take control and move over a few slides. Skip over a few slides.
All right, let's see. All right, can everybody see the ACDC slide?
Yep.
Yep.
Great. Okay. Hello, everyone. So ACDC is a automated Campbell diagram code. That's what it's short for. This is a GUI application that automates the generation of Campbell diagrams. Jason mentioned them briefly in the previous slides. So what is a Campbell diagram? It graphically relates the rotational speed of the rotor to the turbine's natural frequencies and damping. You can see the little plot down here. We'll get more into that later. So what does the ACDC workflow look like? It imports OpenFAST models and then runs OpenFAST in the background to do all of the analysis and post-processes the results. The user defines a range of operating points, combinations of wind speed, rotor speed, blade pitch. Then ACDC will generate the OpenFAST input files for each operating point and run all the simulations in parallel. And then post-processing the results, loading linearization files that OpenFAST outputs, runs the multi-blade coordinate transform, eigenanalysis, gets the natural frequencies, damping, and the mode shapes, and then connects the similar modes across the operating points to generate the diagram. So what are the advantages of this? Because we have lots of toolboxes to generate Campbell diagrams. For one, it's got a somewhat user-friendly graphical interface. It has several new methods for connecting the modes, which seems to perform pretty well. There's the Campbell diagram itself is interactive and you can click through it and it will display various pieces of information. But the most important thing, or that I'm proud of, is the 3D visualization of the mode shapes, which you can see here on the right. It'll do an animation, and you can basically click any of the modes in the Campbell diagram and say, visualize this, and it will generate a little animation like this that will show you the motion of the blades and tower, and along with like the path of the node, the nodes in the model through that mode shape oscillation. So how do you get ACDC? It's available on GitHub. There's releases. There's executables for Windows, Mac, and Linux that you can just download and run. And then there's a link to the documentation, which is 90% complete. All right, and I'm going to do a real quick demo of it for you guys. So hopefully, there we go. All right, so you download it, you get the app for Mac, or you get a Windows executable or a Linux executable, and you just run that and it pops this open. You can create a new project or open an existing project. For time's sake, I'm just going to open up one that I've already got, and it will display, a little bit of information about the project. For the model, this works by importing the FST file, and then from that it will import all the other relevant data. Once you import it, it does not use those existing files, so you kind of have to do any editing through the GUI here. To get quickly to a linearization setup, you can just click defaults, and you'll see some of these things changed to what we consider somewhat basic linearization settings, but you can also come down here and look at any of the files and relevant fields that you may want to change while doing the analysis are specified. All right, next part. You have to define the operating points that you want to use. So things like minimum RPM, maximum RPM, number of operating points you want to generate. You can have a table here where you specify all these values. For this particular simulation, there's no aerodynamics, or for this analysis case, but you can also define structural plus aerodynamics, in which case you have to define a trim gain, wind speed, number of operating points, and the curve. The curve can also be imported from a CSV file, which is useful when you have a lot of data. But this is what this particular curve looks like for the NREL 5 megawatt land-based turbine. And as you'll see here, the blade pitch curve and the rotor speed curve versus wind speed. These are the points in the curve that are specified, and then the operating points are shown via the line. All right. So then you come over here to evaluate, and you want to actually run the simulations. So you select which case you want to run, you click start. First, before that, of course, you need to select the OpenFAST executable. This has to be on your system already, and the version of the OpenFAST executable needs to match the version of the input files that you're using. I tried to make it somewhat OpenFAST version agnostic, but this has been mostly tested with the 3.5 series. All right, as you can see, I set it for 7 CPUs, and it ran all these simulations in parallel. Shows the progress during the simulation and then during the linearization steps. If there's an error or something, you can always click on the log, and it'll pop up the output file, and you can see like what went wrong or just see how long it took. Right. So once these have been completed, you can click on results, click on which thing you want. For the analyses that are defined inside of ACDC, you can just click on the folder. This also works with linearization files that you may have generated outside of ACDC, in which case you would click Browse and just open up the folder that contains linearization files. So with the folder selected, process the linearization files, and it will pop this up, and you have things like, you can look at all the natural frequencies, damping ratios for all the modes in that operating point, which is kind of cool. Then generating the Campbell diagram. This one only had 6 operating points, so there's not a whole lot of data here, but this is your basic Campbell diagram. You can filter by frequency, min or max. There's a special feature called spectral clustering, which can be used to kind of iron out problems if you have like crossings in modes, or filtering out non-structural modes. And so then now you've got these lines, but you don't actually know what they are. So you can click on this, click on any of the mode operating points here, and it will give you the information for it, which line it's on, all the data associated with that mode, and you can click visualize, and you can see the turbine wiggling back and forth. The scaling is controlled here, so this doesn't show a whole lot of motion. You can just click visualize again after changing the scale and see that happen. Another nice feature is if you want to click one of these and visualize the entire line, maybe you want to see if there's something that changes across it. You can come down here and say visualize line modes, and it will load all of the operating points across that entire line. And so you can quickly check and see if they all look kind of similar. Yep. From there, you can also, if you don't want to see them, you can hide the node paths and see just the wiggling shape of the turbine. So this is how you identify the various modes. Then you can come back up here to the line and say, you know, this is flap-wise regressive, perhaps second flap. And that will update the labels here, and then you can export all of the data for the Campbell diagram using this button, export. Real quick, for a case with aerodynamics, it will do all the plots versus wind speed. And then these dashed lines being the a multiple of the rotor RPM speed. So we've got like 6 times and 3 times and 1p, 1 time the RPM of the rotor. So you can see where these potential crossings are, what the frequencies are, and so on. Let's see. This is a little bit slower because there's aerodynamics involved, but yeah. All right, and that's it for ACDC.
Thanks, Derek. That's very cool. Sorry, I just need to share the slides again. One sec, Dan. Yeah, for some reason they're gone from the Teams option to share them. So let me just download them quick, and then I can share from my screen.
Do you want me to load it up? I've got it somewhat handy if you want me to do that, and you can load it up in the background.
It's somehow now it came up, I think.
Cool. All right.
Teams taking me through a loop. Do you see it okay? And just, yeah, as it should be.
Yeah, I do. We're on the slide 40.
All right,
Here we
take
are.
control. And it's
There
all
we
yours.
go. Something happened here.
I see the ROSCO slide.
We're seeing it.
Oh, okay. I don't see anything, so I'm a little blind here. But I can keep going on. So you see the first ROSCO slide? I actually don't see anything, so I have no idea what's going on.
You see the title slide.
So
Okay,
I just
now I see the
took
title
control. Yeah,
Okay.
maybe now if you take it again, maybe it'll work out. If not, I can always toggle the slides for you.
Okay, now I think it's looking all right.
Okay, cool.
There we go. Now we're on to my first slide. Well, thanks, Ralph, and thanks, Derek and Jason. My name is Dan Zalkind. I lead the development of ROSCO. That's our reference open source controller. So the main goal of this is to provide something that's flexible, something that's open source, and that mimics kind of the common functionalities of modern OEM controllers. It kind of has two main goals. It's really for, control researchers to compare their designs against, and also for non-controls designers to kind of use in a variety of engineering studies if they don't have their own controllers. So we've used this on turbine models from 500 kilowatts all the way up to 22 megawatt models now. And I would say that most of the users kind of fall into that second category. They really just want a controller that's pretty darn close to an OEM controller, but they don't have one of their own. So, but we're also trying to do some things to really also make this a useful kind of test bed and comparison for really driving turbine controls research forward as well. We also have within the ROSCO repository this ROSCO toolbox. This is a Python-based tool for tuning controllers, and so it's going to take turbine parameters, so things from the OpenFAST model, a few things from the OpenFAST summary file. We can generate CP and CT surfaces within this ROSCO toolbox and use these as inputs to a tuning procedure where with just a few tuning parameters, things like pitch control bandwidth and our peak thrust, we can come up with like the whole list of gains and set points that are in these DISCON files. So there's probably, there's like 100 lines in this DISCON now. So every time we add a feature, we add some new inputs, but they can be rather detailed and specific to turbines. So we really try to make this ROSCO toolbox a way to simplify that whole process. So kind of give it an OpenFAST model and a few parameters, and you should be pretty close to the, a controller that works. Also within the ROSCO toolbox are a number of kind of file IO, so we can run OpenFAST simulations within the ROSCO toolbox, and there's other kind of helper functions for analyzing and looking at controllers. So the ROSCO software itself is this Fortran-based code, this bladed style dynamic library, and really the only thing that goes between ROSCO and OpenFAST is what's called this AVR swap. So it's an array of floating point numbers, and essentially it's just taking a few measurements from OpenFAST, things like the generator speed, the power. It has a measurement of like your hub height wind speed as if we're coming from an anemometer. It has some loads on the blades, and it has accelerometer data. But then ROSCO pretty much only feeds back the blade pitch on each of the three blades, the generator torque, and then the cell yaw rate. But within ROSCO, we can, use just that limited set of measurements and those limited control inputs to do a number of things. So I kind of listed them all out here. These slides are going to be shared, but these links are all to examples within the ROSCO repository. So for every new module or feature that we make up, we try to make an example that demonstrates it. So, we've got this pitch saturation or peak shaving. So we've got an example that will show, how to set that maximum thrust or the fraction of thrust compared to what the maximum would be. And then it'll show you what this blade pitch versus wind speed and a minimum saturation limit looks like. We've got, similar things for our floating feedback. We've got a number of different ways to tune that. And so these examples kind of show the different ways. And so they're nice starting places if you, for instance, want to add some of these features to your turbine simulations. Some of the newer things that we're pretty excited about are, this tower resonance avoidance. Folks have been asking for that for a while. So it's going to skip rotor speeds that have, resonance in them. So, if you use Derek's ACDC tool and you see that, your 3P frequency is crossing over one of your tower modes, you'd put that into ROSCO as this rotor speed to skip, and it would kind of avoid that rotor speed area. We are working on some like variable speed set points, so you could do like a soft cutout. We have cable and structural controls. So like Jason was saying, you could change mooring lengths. You can change properties of tune mass dampers in your OpenFAST simulations. And then we've got a number of ways to kind of interact with other software. So the 0MQ is a way that kind of external, like a wind farm controller, can interact with ROSCO kind of externally. And then we've also got some open loop controls if you just need to debug some of your simulations. It's a helpful tool. So next I'm going to show just kind of a demo of how we optimize a floating wind turbine controller. Floating control modules that are of interest for us are, this pitch control. We know that there's kind of this trade-off between how fast you can control a turbine and this floating motion or this kind of negative damping problem. We've got this floating feedback, which kind of takes the nacelle acceleration and feeds this back into an additional pitch input. Our peak shaving is really important for kind of maximum thrust on the rotor, which kind of creates our maximum pitch offsets, which really starts these instabilities. And then individual pitch control is another one, especially for large rotors. But also if there's a lot of yaw motion in the platform, you can use individual pitch control in order to kind of smooth out some of this floating motion as well. So here's an animation. This is happening actually within WISE, which is a, an optimization software, which is going to run, a whole bunch of design load cases in parallel. I'm showing all the design load cases here in the middle, but on the right is one OpenFAST simulation. And so what's happening is we're changing our bandwidth and our floating feedback in order to kind of get our overspeed or our maximum generator speed below this dashed line. And then we're trying to minimize our tower damage equivalent loads. And so this is kind of my tuning procedure for pretty much all turbines. If I were to do this for a fixed bottom turbine, I'd leave out the floating parts. But really the goal is the same. It's to drop these tower damage equivalent loads, which I'm showing here in the middle, and then this horizontal line is kind of the lifetime of that. And so we want to drive that bar down, but we want to do that by, also keeping these generator speeds below this maximum allowed limit. And so there's also some examples of this on the WISE repository. You kind of just give it your OpenFAST model and you set, these design variables should already be set up. You need to tell it a little bit more about which cases you want to run. Here, I think we're running just normal operations, 6 seeds for each. And then it'll run all these cases in parallel if you've got the resources and do all this automatically and solve it using some of the optimization solvers we've got. So just looking ahead in ROSCO, I'm working currently on this power reference control. So if you need to like derate your turbine or even simulate power boosting, you can do that through changing your speed set points by changing your maximum torque, or also changing your kind of fine blade pitch if you want to derate across all wind speeds. We are working on some additional floating feedback configurations. There's a way to do it with both the torque and the pitch control. And then the next thing that we're kind of working on that I think is kind of big, and it's also funded by this WISE project, is support for all IEC design load cases. So right now, ROSCO is pretty much just an operational controller, but we're working on some additional like startup, shutdown routines, maybe some condition monitoring, and ways to really control the turbine that are pretty straightforward for all the IEC DLCs, so we can do kind of these full suites of simulations. Kind of looking forward into the medium term over the next year or two, we really want to also kind of put out this test bench for controller performance and quantification. So, folks are starting to use ROSCO as a comparison for their controls, but still folks kind of compare things in different ways and different cases and with different cost measures and different constraints. So we want to also try and put out there like maybe a standard set of cases, maybe some standard cost measures and constraints, ideally informed by the users or similar things to what the OEMs are doing, so that when people put out controls research papers, we kind of all know that we're playing the same game at least. One of the main funding sources for ROSCO is our controls project, which does a lot of wind farm controls. So, I think that we're also looking into ways to kind of bridge the gap between turbine controllers and wind farm controllers. Wind farm controllers often assume that you can yaw the turbine however you want, but in reality, these turbines kind of need to also protect themselves and point themselves into the wind. So looking into ways of kind of bridging this gap. And just overall, we're looking into kind of identifying and reducing gaps with OEM controllers so that folks that don't have access to those have pretty good stand-ins. And then another one of my ambitions for ROSCO is really to make this a little bit more modular, maybe even rewrite the code outside of Fortran so that folks can add community solutions a little bit more easily, and ROSCO can kind of be continually improved over time. So that's all I've got, and I'm happy to turn it back over to you, Raf.
Great, thank you very much. And we'll actually pass it to Jason to summarize the roadmap. So yeah.
Thank you. I'm not sure how to go back here, but I'll just jump over before we jump to the polls what I skipped earlier. Yeah, so talking about the roadmap of where we're going, I would say that we really have four main pathways on the software development side to improve OpenFAST. One is on the area of improving accuracy, using data or HFM results, experiments to make sure that the codes, particularly aerodynamics or hydrodynamics, are getting more accurate over time. Also looking at advanced technologies, anything that's coming out with new sensors or actuators or novel concepts, like multi-rotor systems, being able to support those things. We're working a lot trying to improve the way the tool is used, things like ACDC and ROSCO, and how to do, multi-fidelity type simulations. And then another big part of our approach is how we approach, supporting users and also developers, trying to make OpenFAST really not just an NREL-centric tool, but also have being able to support community contributions. In terms of the software quality, I would say we've looked at it and we've sort of graded OpenFAST through a rubric on a number of areas, from accessibility, usability, documentation. We certainly understand right now with OpenFAST is a mixed bag. Some things are really well documented and some things are not well documented at all. And so, extendability, community health, these are all things we sort of graded on. I would say OpenFAST in our grading system has gotten fairly a medium. Some things are really well characterized, and some things are not treated very well. We'd love to work on improving that. And this is kind of where we're hoping to get some feedback today, also where we want to focus moving forward. In terms of like physics areas where we want to move forward, these are sort of my top list of areas that fit on one slide. But I'm curious about what your opinions are. So one area that we've been pushing is being able to go better from global to local. So global being like a beam type model like OpenFAST. Detailed structural analysis, quite important, for the blades or the substructure. Viscous hydrodynamics is a thing we've been tackling a lot recently, trying to make, the viscous part better. Steep and breaking waves is always a big challenge offshore. Floater-induced aerodynamics, another big challenge. How you combine things like rotational augmentation, unsteady airflow aerodynamics challenge. Of course, as you get to larger rotors, high Reynolds number, up to 20 million becoming a challenge. Stall and vortex-induced vibration, big thing for aerodynamics on parked or idling rotors. complex terrain for wind farms, things like air-sea interaction, how to treat things like atmospheric stability in the design, and tropical cyclones. And then as we get to larger farms, blockage, deep array is becoming more important, and things we'll have to do. Let's see. And then I just want to mention two things before we go to the poll, or Paul. Yeah, I think it's maybe just worth touching on this briefly, just saying, you know, there's two ways to engage with us through open source. One is through our forum, one's through GitHub. I think most everyone's familiar with those two techniques. Of course, if you're an industry member and you're willing to pay for support beyond this general support, we're happy to do that. And just to be clear on how we get funded for this work, we really have four ways of doing this. As Rolf mentioned, you know, WETO provides a lot of sort of the backbone for work, but we also do a lot of things through competitive solicitations through, for example, WETO or RPE. Now RDC is a common one these days, as well as BESI. We do offer direct industry support contracts, technical support services, basically, whether that's on code development or application or validation. These are the list of the current industry players that are funding active development of the tools right now. And we definitely appreciate those partnerships. Another thing we've been pushing is basically to offer, you know, there's quite a few consultants that make advantage of tools like OpenFAST and their consulting services. And we're trying to set up partnerships so we can basically offer the back-end support where we can, you know, do further development and validation of OpenFAST and solve sort of research level challenges that these front-end consultants are facing. So I just wanted to give that background and then pass over control now to Raphael, who will take over with our polls.
Yeah, thanks. All right. So yeah, thanks to Jason, Derek, and Dan for that nice overview of all these tools. And yeah, now we want to just go through a chance to get some direct input, some kind of guided input from you. And so in past workshops, we've used the Teams polling, and as we saw earlier, that has not worked out very well. So we're trying this new system here, or new to us, called Mentimeter, and it's a bit more interactive. So just to start, for you to get to the polls, you can scan this QR code if you have your cell phone nearby, or if you go to this website, menti.com, and then enter this code, you'll go to, there'll be kind of a holding screen first. So I'll give us all a minute to do this. And this instruction here at the top will stay there through all the rest of it. So, assuming we're nearly there, then on my end, I change the slide, and this should change on your end. So either on your browser, on your computer, or on your browser, on your phone, and then you can respond to the polls here, and we'll start to get some results here live. So. Our usability is the strongest, or yeah, highest priority. All right. Yeah, well, ClearLeader is improving usability, so that's good to know. I'll move on to the next slide here. Given any advanced technologies that are not currently supported in OpenFAST, which would you like to model? And this is a word cloud, so you can enter just a few words, enter your response in just a few words here. This is really interesting. So some of these things are supported already in OpenFAST, and so I wonder if, or well, in the OpenFAST ecosystem. So I wonder if maybe just maybe that ambiguity about whether these things are well supported is answered through this workshop. Jason, do you have anything to add based on what you're seeing here?
Yeah, well, I'm happy to see some of them are definitely things we're working on. So wakes, of course, we can do wake effects now in Fast Farm, and if you want to, if that's really about single wakes, I think tools like Olaf and our free vortex wake model are making that better. Happy to see multi-rotor. There's looks like multiple people interested in that one, as it's standing out a bit more boldly. We are working on that, as I mentioned. Not exactly sure what is meant by induction, because we do have, either BEM or free vortex wake for induction. So hopefully that's already covered, but I'd love to get clarity from someone if they want to comment what that is. Drive tower torsion, definitely that is in our pipeline. I think we have it planned for next year, maybe the year after. We do have funding now for that one. I know that one's been a limitation. Blade pitch actuation as well. There definitely that's also coming soon. Drivetrain, that's a good one. I've been trying to find money for drivetrain dynamics for a while, and yeah, don't have a great solution yet, but love to talk about how we can make that happen. Definitely hear things there about high accuracy of aerodynamics. Actually, we have another question on that one coming up, but definitely aerodynamics is definitely an area where we always see that there's need for improvement. Wind speed based cutout, I think Dan Zalkind mentioned that one in ROSCO. It's definitely something that's coming.
It looks like Dan Hook has a question.
Yeah, hey Jason, I put induction in. Yeah, to my knowledge, there's not any way to affect your inflow through induction effects.
Oh,
Like
this
that,
is like
that
the
coupling.
upwind.
Yeah,
the
the upwind
upwind.
induction zone, exactly.
Yeah, maybe that's tied to what's blockage there as well.
Could be, yeah.
So that's a good point. That's definitely something we've talked about, at least at the farm level. Quickly as you get to larger farms, that's becoming much more important. Maybe you're interested in like things like a forward-looking LiDAR and want to see the effect of that in OpenFAST. Definitely, thanks for clarifying that.
Yeah, so it definitely came out of raw in a lot of ways,
Yeah,
trying to make different inflows, but depending on where your measurements are, you have to consider the induction and essentially remove it before you feed it in.
Great, thanks for clarifying that. Definitely
Thank
important.
you.
All right, great. We've got another similar word cloud question. How would you like to see the usability of the OpenFAST ecosystem improved? You're good. Looks like there's quite a bit of accessibility points here. Seems like maybe there's a little more passion here than the previous
a lot more variety too. Not fewer things standing out as bold. So Yama looks like it's standing out as bold.
Yeah.
And so multiple people have been saying that one. I think what our push for there, the WISE tool set, being able to use the Wind.io framework. which is all YAML based. And so we have that capability if you're using WISE. I think what we're missing maybe right now is to be able to go from OpenFAST model to a YAML file. So we can go from YAML to OpenFAST. What we can't do is go from OpenFAST to YAML yet. I'd love to have that in there. Better documentation I see as bold, definitely. Again, as I mentioned, I think some things are really well documented and some things are very outdated or lacking. And so I totally agree with that one.
What is robust VLM? So I'm just not familiar with what is VLM.
Someone wants to comment on that. I see speed up of beamdyne in there. That's definitely coming with our tight coupling scheme. That the whole point of tight coupling was to make beamdyne models with beamdyne and models with subdyne much faster. And so that's definitely coming in the 5.0 release here in September. Definitely, I see some things there for learning and training, you know, GUIs for students, demos, tutorials, getting started guides. We definitely have introduced some improved things in the 4.0 release. We have basically a getting started guide that's been introduced in the documentation that kind of goes through a lot of the issues initial users of OpenFAST experience, and hopefully that gives some guidance there. But I definitely agree, more work in that space would be useful. We are, maybe you also mentioned, we are going to be hosting an OpenFAST workshop in a WinTech conference, and we use that for both overview material and also a hands-on portion where we step through. And I think as Emmanuel Brandlard from UMass leads that hands-on part, and he really bases it on a video game analogy. We're sort of leveling up. You know, if you're at some level, how do you make yourself better? And that's quite good. So please come to that if you're interested in really diving into OpenFAST and learning more.
Okay, yeah. Well, this is really good feedback, and I think they kind of fall into distinct bins. So we can take this and yeah, work it into how we plan these tools. How have you gotten successful user support in the past? So this is, yeah, just give your input. It could be all of them, none of them, or some subset. I guess there's not an option for none. It's just not vote.
Dan Hawk says left out colleagues who know more than I do.
Good point. Okay, so yeah, actually, this is I think a closer distribution than I expected, as in more flat than I expected. So most
advocacy software documentation stand above there.
Yeah.
I always feel like we write that and no one ever reads it. But that's great that people are saying actually read it.
Yeah. And the examples, I assume that's the regression test examples. I kind of included that generically to match the polls from other workshops. But yeah, anyway, that's also good to know that people are referring to those. And the NREL forum is something that has come up also in other workshops as a possible resource. And I know that's mostly related to OpenFAST and this ecosystem of tools. So it's good to see that that is highly represented here. So given this, a follow-on question is, how would you prefer to get user support in the future? Yeah, and these are just a few options here. Maybe we're going to come up on an open discussion question or open discussion section later. So if you have other ideas, you can bring them up there. A lot of support for a workshop. Just to respond, while more responses come in, just to respond to Meg's question here in the chat on what that Jason mentioned, that there's a workshop that Emmanuel Brandlard will be giving at NOWEA, and Meg asked how to get information on that. So in the process of these workshops, of putting together these workshops and getting the word out, we've been talking about how we do that for this collection of tools, not just OpenFAST, but the WETO Stack in general. And so, yeah, I think as a consequence of these and talking to the community, something that I'd like to work on between now and really the timeframe for NOWEA is putting together either a mailing list or some sort of communication mechanism that broadcasts widely on the WETO Stack. And that's the sort of thing that the information on that workshop and the other NOWEA workshops, because there's a whole series of them, is exactly the sort of thing that would be included there. So for you specifically, Meg, we'll certainly, we're in contact with you quite a bit, so we'll certainly get you that information. But also just more generally, if anybody feels like an email list or a newsletter is or isn't effective, I'm curious to hear your feedback. And if you have any other ideas for any maybe more effective methods for this, I'm also curious to hear your feedback. We only advertised this on LinkedIn, and the word got out, but I think it actually spread quite a bit through word of mouth, which is effective. But you know, ideally, we'd like to connect with people more directly. Okay, great. Well, it seems like Mentimeter worked out, so that's a win. And yeah, now I'll just open the floor for just a general discussion on the OpenFAST section. So you've got Jason, Dan, and Derek here to answer any of your questions. And also, yeah, this question that I just posed on communication and the workshops and the WETO Stack in general. Looks like we've got a question. Meg, go ahead.
Hello, continuing my streak here. Yeah, I think just around your communication question, I think like what Dan said in the chat as well, an opt-in email list would be good, but I think also just trying to then surface anything from within that email to somewhere just online accessible, and like a summarized point would be good. I think one of my personal complaints about email is that it only really helps the people who are involved in that particular chain. But and then I guess maybe a question more to, well, I guess maybe just question / suggestion. So like Dan, for instance, when you were showing the ROSCO example, I think I've been looking for that kind of capability, and I'm definitely not a controls engineer, so that's probably strike one. But of like how to, we've been even just struggling with trying to keep like rated power consistent, and not just make a 250 kilowatt machine a 2 megawatt machine. So I think just maybe to try to stop rambling here, trying to provide some examples of how if you have a new model or you've made a change to an existing model, like what's the recommended workflow across all of these tools? Like, do you first want to run a Campbell diagram? Do you first want to run some open ROSCO tuning? You know, what's the kind of recommended flow from kind of new model to, you know, maybe you either run a batch script or go to WISE eventually to run full DLCs?
Yeah, I think that's totally valid. Everybody has their own workflow a little bit. I wasn't able to edit my new turbine controller screen capture in time for this, but yeah, I typically kind of start with something nearby, change a few of the parameters, and then run it in steady state. Start simply. For all of the NREL tools, I feel like they work, and I like to change one thing at a time, and then you can kind of be confident about what thing that you did broke it, rather than changing too many things and then having to back up. But yeah, I think that's totally reasonable request, and kind of liked the video format too. I might keep pulling on that thread and posting on our docs.
Awesome, thanks.
Yeah,
Yeah, I think videos are useful too. Sorry, I think it kind of helps show the workflow. Like these are helpful to get overviews of the software, but the actual like how do you actually make that what you showed happen is a helpful level of detail.
Yeah, that was one intention for these workshops, to kind of concretely show what this software is. So we can talk about it in the abstract, but to literally show how to do it was something we were hoping to achieve. And I'm not sure if certainly in one of the earlier workshops, Meg, I'm not sure if it was you that brought it up, but we've had this same topic come up about how these tools at a high level fit together. So it's kind of, well, we've identified already how they fit together within specific workflows that are like very maybe contextually more narrow, but more broadly is something that, or that perspective more broadly is something that came up earlier. And I think it's a good point, and I think it would be nice to try to identify that going forward. So thanks for bringing it up here again. If there are no questions from the audience, I've got maybe just to put.
Sorry, I put one in the chat, but I can just ask it.
Yeah,
I was just wondering if you could just talk about how you guys approach backwards compatibility. I think including or maybe especially for softwares that have to couple, like OpenFAST AMR. I don't know. I am not a software developer, and I'm a novice user at best here, so it may be the worst kind of person to ask questions about this stuff, but I just am aware that it's been an issue.
Trying to see if Andy Platt's on the call, because he could probably at best. Yeah, Andy is on the call. Oh, can I put you on the spot, Andy, and have you answer that one?
Sure. So one of the things that we're looking at doing going forward is actually supporting some of the older versions. For example, like our 3.5 series is being will continue to get support even though we've moved on to a 4.0 or a 5.0. So we intend to keep like the 3.5.x support, including like bug fixes that will backport to it. In terms of being able to read older input files, that's not something we currently have the manpower to be able to do. It's something that would be nice. I think going to a YAML type input file would probably better support that, but at the moment, that's not something that we can really support.
And then in terms of ROSCO, as of like version 2.8, a lot of the inputs are now optional. So like if you have an older version, it should, work with kind of newer versions, and then defaults will be filled in for kind of the new features that you don't necessarily want. There's a script for updating versions. And then for like OpenFAST file IO, I think the direction we're heading is actually to include that file IO with the OpenFAST repository. So like we had a set of readers and writers within WISE, but then like if OpenFAST updated their inputs, WISE would then need to update those. And so these things need to be compatible, but if they're all kind of within the OpenFAST repository and then OpenFAST increments, those file IOs should also increment. So we're hoping that that's a kind of nice solution to be able to keep track of versions for file IO. There's a question. Go ahead.
Oh yeah, go ahead.
Well, there's a question in the chat about how to make one's own DLL. I'd start with, the ROSCO documentation on compiling the ROSCO DLL, and then I'd change it step by step to whatever you want it to be within the Fortran code would be my advice. I don't know, that's not like, specific advice, but yeah, I'd say start with something that works and incrementally make changes.
I've got a question on the OpenFAST toolbox. We didn't talk about it explicitly, like we didn't have a section here to talk through that, and Jason mentioned it. I know there's a lot of things in there. Maybe Andy or Derek, are either of you willing to just give a very brief overview of maybe what's most useful there for you, or yeah, just any idea of what the capabilities are there? Maybe not. Or Pietro.
Oh, I'll go back a second to the previous question. I guess
Yeah.
Maybe then the question was more like, how is the swap array built? And that's something that over the years has always been a little surprising, but it follows the bladed swap array from decades ago. And so the swap array is this array of data interfacing OpenFAST to, or an Elastic solver to a controller, and it has a specific structure that is documented in the bladed user manual. And so ROSCO uses exactly that swap array. And so if you want to use a different controller, you can just, as long as you follow that swap array, then you should be good. And yes, you can start, as Dan was suggesting, from ROSCO and see how ROSCO populates that swap array. And then you can just, swap ROSCO out and swap something else in.
Thanks, Pietro.
Yeah, there's also several simpler Fortran controllers in the OpenFAST R test that use the same swap array. There's pretty good documentation in OpenFAST about what that swap array layout looks like. Those are all good sources. As for the OpenFAST toolbox, there's a lot of utilities for reading input files, writing input files, doing linearization. The multi-blade coordinate transform is included in there. I think there's also things for reading like the aerodynamics files and stuff like that. That particular library was maintained by Emmanuel Branlard, who has left NREL, and so we're kind of still looking for who's going to be maintainers of that software.
Another big thing in the OpenFAST toolbox is FastFarm scripts for how to generate FastFarm models and generate inflow for FastFarm. Those are the big sticking points with FastFarm, is how to set up the model discretization and the inflow generation to make sure they're consistent and follow all the guidance. So the OpenFAST toolbox has a nice set of scripts that automate that process for you. So any users of OpenFAST recommend you, a FastFarm recommend you use that toolbox.
Great.
There's a Python one and a MATLAB one, or is it the same?
So we named Bonnie's here in the room. She was asking about MATLAB versus Python. So we used to have what's called the Python toolbox, and that's been replaced by the OpenFAST toolbox, but effectively it's OpenFAST toolbox is a Python-based set of libraries. The MATLAB toolbox is another thing there. It's a little more outdated these days because a lot of NREL people have switched to Python, but yeah, a lot of the pre and post processing scripts are also available in MATLAB through the MATLAB toolbox. Like Anurag is asking about how to broaden the OpenFAST development community. And this is a great question. Thanks for asking that. And I try to at least say how we see it at NREL in my last slide that I presented. I would say is, definitely core work in this area gets funded by direct funding by Department of Energy, but that's probably only a small portion of the overall effort in OpenFAST development. And we're definitely encourage going together on solicitations for partnering with NREL and partnering with the community to advance the tools. Want to make it clear we also are available for offering direct technical support services. We do this with a number of clients already. So if you're an industry member and you want more direct access to NREL staff and capability, or you want to take the tool and help you advance it, happy to do that. Obviously, if you're PhD student and you're working on any sort of code development that may involve an OpenFAST change, really have set up OpenFAST as a community model. So I think the process for contributing code advancements is quite clear in the documentation and through the GitHub infrastructure. So yeah, we definitely encourage external contributors to fork OpenFAST, make some change, make some improvement, and then share that improvement back with us. It's always good if you're in that mode to have a quick conversation with us. Tell us quickly what you plan to do, and we can probably give you some pointers to make it easier along the way. But the overall process is, mechanics of that process are laid out clearly in the documentation. Happy to have any other comments on that. If you want to say anything, but thanks for bringing that up, Anurag.
I think also the OpenFAST toolbox could be a place where sort of like that, it's like a low barrier to entry to contributing back. So if you have scripts, so that doesn't have it's kind of a loose collection of tools. It's not this huge package that, that has things that need to fit together throughout. So especially things that are pre and post processing from the community, that seems like a logical place to bring them back. I think it's in this limbo right now, like was mentioned, where there's not one model owner for that. But yeah, we're thinking through how to resolve that.
Thanks, Raf. I think, yeah, Garrett has a similar comment in here, right? So there's this core physics development, which is trickier to integrate, but all the ecosystem pieces, right? If there is a lot of communication, either in, I don't know if you guys already have the forums in place to have that communication. I've seen multiple organizations essentially replicate stuff around OpenFAST. Some of them are good, some of them, but it's all in the end a waste of time, because somebody's already done it, and the likelihood is somebody's probably done it better. And so I think it'll be a good resource for everybody to kind of collapse around one or two, and then where the NREL team can put the finger on the scale to see which one fits better into the overall ecosystem, which one comes closest to your ideas on structure, architecture, etc. And if you quote unquote bless it, right, and then it becomes something that the entire community can keep going on. And so you don't have to deploy expensive or rare resources on, say, converting a code from Python to C++, because now all of a sudden it can run 8 times faster, right? And all those things will be, I've seen plenty of students love to do stuff like that for grad students. That's the kind of thing that's wonderful challenge. And if you can get, yesterday or day before yesterday, we're talking about acknowledging them in the broader community, right? So lots of useful contributions can be acknowledged that way too.
Yep, a lot of good points there. I think there's a lot of opportunity for especially this ecosystem, because it's so widely used and through a variety of experience levels that we can. I think we just haven't done a good job of like coordinating these things, but I think we can encourage that contribution to come back.
Yeah.
I also just want to call out Meg's point in the chat about how if there are scripts to what did she say? If there are scripts to run a power curve or any other kind of sweep using YAML inputs, that they're not easily findable. And yeah, thanks for pointing that out, Meg. I think that's a good point. I know there are some things in Wise, right, Dan?
Yeah.
So there are some examples there, but maybe that's not as yeah, maybe it's not as findable when you don't already know that it's there. Okay, well, we're coming up on time. I see some pretty good comments in the chat about generally kind of yeah, defining these workflows, a cheat sheet approach. Yeah, I think these are really good suggestions, and we'll certainly take that and chew on it and see how it looks, you know, how we can start to achieve some of these things on our end, and especially lead the community to build it all together. So if there's no other pressing questions, then we'll wrap it up. So yeah, I just want to thank you again, everybody, for presenting and for joining, staying the full 2 hours till the end. Like was already mentioned, you can engage with this group of tools through GitHub issues or discussions or the NREL user forum. This is the link, forums.nrel.gov. And then the software repository links are also just listed here, but I'm sure you all probably know most of those. And then lastly, I'll just point out that all of the materials for these workshops are being hosted on this website, nrel.github.io/WETO Stack. And so the materials are the slide decks themselves, PDFs of the slides, and links to the recordings that are put on YouTube. So there's a distinct section for each workshop, and so you can look out for that. And then there's also going to be a summary report that'll be posted here within the next couple of weeks. And yeah, if you, I think I've said this in all of the previous workshops, if you have any feedback on the format of the workshops, what might make it more useful or more practical for you as an attendee, please let me know. You can email me at this email address, raphael.modefort@nrel.gov. I'll also send a follow-up email within the next couple of days with a feedback form there, and you have the opportunity to submit anonymous feedback. So please take the opportunity to do that, because we intend to make these a more regular part of our workflows, of our development flows. So yeah, your feedback on how to make it better is really important. So with that, yeah, thank you everybody for joining. Jason, does anybody else want to say any last thing?
No, appreciate the feedback, and we'll take that into consideration going forward.
All right, great. Thank you, everybody.